Welcome to this session on CCNA Tutorial, Network Fundamentals. This video is aligned with Cisco's official CCNA 200-301 exam blueprint and is designed to guide you step-by-step towards certification success. In this lesson, we cover Section 1.10, Verify IP Parameters for Client OS. Let's start by understanding what this section is all about. When we verify IP parameters, our goal is to make sure each device has the correct IP settings, like its IP address, subnet mask, gateway, and DNS. This is one of the first steps in any troubleshooting process. Throughout this lesson, we'll compare how to check these parameters on different operating systems: Windows, macOS, Linux, and Cisco IOS devices. By the end, you'll know exactly which commands to run and what the output tells you. The OSI model, or Open Systems Interconnection Model, is the foundation for understanding how network communication works. It breaks everything into 7 layers, from application down to physical. Each layer serves the one above it and handles its own specific tasks, like addressing, routing, or delivery. We don't actually implement OSI directly, but we use it as a guide to troubleshoot problems logically, one layer at a time. Here's a quick look at all 7 OSI layers from top to bottom. At the application layer, we have user-facing services like HTTP, DNS, and DHCP. The presentation layer handles data format and encryption, things like SSL or TLS. The session layer manages communication setup, while transport ensures reliable delivery with TCP or UDP. At layer 3, the network layer uses IP for routing. Layer 2 handles MAC addresses and Ethernet framing, and Layer 1 covers the physical media, your cables and network cards. The TCP/IP model is the real working framework behind every modern network, including the Internet. Unlike the OSI model, it has just 4 layers: application, transport, Internet, and network access. It's simpler, protocol-focused, and built around the Internet protocol itself. This model defines how data moves end-to-end across networks using protocols you already know, like TCP, IP, UDP, DNS, and DHCP, the ones that make the Internet actually work. Now, let's compare them side by side. The OSI model has 7 layers, while TCP/IP combines those into 4. The top 3 OSI layers, application, presentation, and session, are grouped into the TCP/IP application layer. Transport maps directly to transport, and the bottom 3, network, data link, and physical, fit into Internet and network access. So, OSI helps us understand concepts, while TCP/IP shows us how networks actually work. Here's how the OSI and TCP/IP layers interact. When data moves down the stack, each layer adds its own header. That's called encapsulation. At the sender side, it starts as application data, becomes a TCP segment, then an IP packet wrapped inside an Ethernet frame, and finally turns into bits on the wire. At the receiver's end, the process reverses. That's decapsulation, stripping off each header until the user sees the original data. Now let's talk about DHCP, the Dynamic Host Configuration Protocol. DHCP automatically assigns IP addresses and other network parameters to hosts, saving you from configuring every device manually. It works at the application layer and uses UDP ports 67 and 68. The process follows 4 steps: discover, offer, request, and acknowledge, often remembered as DORA. On Cisco devices, you can enable DHCP on an interface with the command IP address DHCP. And when a DHCP server is set up on a router, it can dynamically assign IP addresses to clients across the LAN. Next up is DNS, the Domain Name System. DNS is like the Internet's phone book. It translates easy-to-remember names like Cisco.com into IP addresses that computers actually use to communicate. DNS runs on UDP port 53 for regular queries and TCP 53 for zone transfers. On Cisco IOS, we enable it with IP domain lookup and specify a DNS server using IP name server. When you ping a host name, the router will first contact that DNS server to resolve the name to an IP. If resolution fails, you can verify the cache using show hosts. That's the iOS equivalent of NSLookup on Windows. A MAC address, or Media Access Control Address, is the unique hardware ID built into every network interface card. Think of it as the hardware fingerprint for the device. It operates at Layer 2, the data link layer, and helps switches deliver frames to the right device inside a LAN. Each MAC address is 48 bits, written in hexadecimal. The first half identifies the manufacturer, and the second half identifies the specific device. It's stored permanently in the NIC and used only for local delivery within the same network segment. Routers use ARP to map IP addresses to MACs, so when one device wants to reach another locally, it sends a frame directly to that MAC address. The default gateway is the router interface that connects your local network to other networks or the internet. It's usually the first or last usable IP in the subnet, and it can be assigned manually or automatically through DHCP. If a destination isn't local, the host sends the packet to the gateway's MAC address for forwarding. In Cisco IOS, you can set it with the command IP default-gateway, which is the router interface IP address on your local network. If that gateway is misconfigured, you'll lose external connectivity even if your local IP looks fine. You can confirm reachability by pinging the gateway first. It's always the first test in any troubleshooting workflow. A loopback address is a special reserved IP that lets a host test its own TCP/IP stack without touching the physical network. It works at Layer 3, the network layer, and is typically 127.001 for IPv4, or :1 for IPv6. When you ping the loopback address, the packet never leaves the device. It loops internally through all protocol layers, confirming that the TCP/IP stack is installed and functioning correctly. A PIPA, or Automatic Private IP Addressing, is what happens when a DHCP server can't be reached. Instead of staying offline, the device assigns itself an address in the 169254 range. This allows limited local communication within the same subnet, but there's no default gateway or DNS, so it can't reach external networks. Once DHCP becomes available again, the device automatically replaces the address with a valid one. In Windows, all verification happens through simple command line tools. Start with ipconfig/all to view the complete configuration like IP, mask, gateway, DNS, and MAC. If DHCP fails, use ipconfig/renew to request a new lease. Test connectivity using ping, first your gateway, then an external IP, and finally, a hostname to check DNS. If you need to trace the path, trace_RT lists each hop, while NSLookup checks DNS resolution directly. What's different from other systems is the command structure. Each task, like renewing or releasing DHCP, uses a separate switch. macOS uses the same Unix foundation as Linux, but its commands look a little different. ifconfig shows your IP and interface details, similar to ipconfig on Windows, but with extra technical flags. For testing, ping and traceroute work exactly the same, though traceroute defaults to UDP instead of ICMP. In Linux, the goal is the same: verify addressing, routing, and connectivity. But the tools are more flexible. You can use IPADR show or the older ifconfig to see interface info, and IP route show to confirm your gateway. Ping and traceroute behave just like on macOS, but Linux offers more control. You can specify interfaces, protocols, or packet sizes. So, while the purpose is identical, Linux gives you far more depth and customization. Cisco IOS commands follow the same logic, but from the network device's point of view. Instead of ipconfig or ifconfig, you use show IP interface to verify addresses and interface states. Ping and traceroute work the same way as on Windows or Linux, but iOS adds per-hop response times and extended options for testing paths. So while the tools are consistent across all platforms, Cisco adds the professional-grade depth for real network diagnostics. When something doesn't work, always go layer by layer. If there's no link light or Wi-Fi, that's a Layer 1 issue. Check cables or interface status. If the interface is up but you can't reach other devices, check the MAC table or ARP entries. That's layer 2. If you can ping locally but not outside your subnet, inspect your gateway and routing. That's layer 3. If IP works but name resolution fails, it's a DNS issue at layer 7. And finally, if everything works except remote access, check ACLS, SSH configuration, or firewall rules. Always verify in this order: IP, gateway, DNS, path, port. Here, we take that same layer-by-layer logic and apply it to real symptoms. If you see no network access, think layer 1, check cables or Wi-Fi. An interface showing down/down points to a physical or duplex mismatch. A 169.254 address means DHCP isn't reachable, while a duplicate IP is a layer 3 conflict. If you can ping by IP but not by name, that's a DNS problem at layer 7. And if SSH or Telnet fails, the service might be blocked or disabled. Each issue here maps to its OSI layer, and the commands beside it, like ipconfig/renew or show IP route, tell you exactly how to confirm and fix it. Verifying IP parameters isn't just a one-time setup check. It's the foundation of every troubleshooting process you'll do as a network technician. You've seen how each operating system, Windows, macOS, Linux, and Cisco iOS, provides its own tools, but the logic stays the same. Confirm the interface and IP, test the gateway, trace the route, and finally, test DNS and remote access. Once you build this habit, diagnosing network issues becomes fast, consistent, and methodical. That's the key takeaway for this section. Always start simple, verify layer by layer, and use the right command for the right platform. Before moving on, take a quiz to test your understanding. Quizzes, summaries, and slides are available on ccna.academy. If you have any questions, leave a comment below and I'll be happy to help. Up next, Section 111, Wireless Principles, where we'll explore how Wi-Fi works, what defines different wireless standards, and how frequencies and channels affect performance.